Hey guys, a very good morning. Thank you for joining with us. My name is TN Pradeep Kumar Naidu, and we are here to represent Nikit Engineers, which is into welding from the past 42 years. And the kind of knowledge that we have gained over the past 42 years, we would like to share it with you guys to solve a much complicated problems of welding and simplify the entire process. So let's see what we're going to solve today. So guys, the component that we are welding today, or the problem that we are solving today, is of steering cylinder welding. Basically, these are hydraulic cylinders, and you can see the cylinder here. This is just an example. Basically, they have an inlet port, there's an outlet port, mounting blocks, and basically it comes in a single acting or a double acting cylinder. Right. So let us move on to the 3D component of it, to just give you a glimpse of how we convert the drawings into 3D, and then we try to conceptualize the entire machine by understanding the cylinder here. Okay, the cylinder that you're seeing here is a typical 75 dia cylinder OD, and there are two ports, inlet and outlet. There are two blocks, one on the left, that's for basically these blocks are for mounting only. Now there's another view, there's a side view where you can see the bore. Basically there's an end cap also which fits onto the cylinder. So totally we will be welding about three stages. One will be the ports, inlet and outlet. The second stage will be of the blocks, and the third stage will be of the end cap, which is right now not visible. So let's move on to the concept, guys. So this is the concept, basically how we design the entire system, the actual concept. And here you see basically three linear axes, two rotary axes. One is the torch rotary, one is the job rotary, and apart from these two rotary, the linear axes are x-axis, y-axis, and the z-axis. The x-axis is about 500 to 1 meter in stroke. The current system that we have designed is about 1 meter in stroke. The y-axis is about 500 mm. The z-axis is about 500 mm. The torch rotation, we have limited it to 730 to 760 degrees. B-axis, it's a continuous rotary system. So let's move on to the 3D design, guys. Yeah, here it is. Small SAV format that we would like to show you. This is how the torch has been mounted. There's a small rotary unit, torch rotation, for torch rotation, and the cable moves out through a top adapter, so that there's not much of a twisting in the cable, as a cable in this particular system has been tested and it's suitable for plus minus 760 degrees of rotation. Now the entire machine, as you can see, is basically a Cartesian system with two rotary. This machine has been patented. It's a patented technology, patented in India about 4 years back, and in Australia just about 3 months back. The system that we have patented is complete Cartesian robo, along with the kind of program that we are using. Basically it runs on a motion control platform. The platform that you're seeing right now, the base platform that you're seeing right now, is a tabletop one. We'll be mounting this to a particular frame based on the customer input. There is a 7-inch display onto the left side. Most of our systems, what you can observe is all our displays are on to the left, so that operator has got a feasibility onto his right for loading and unloading of the component. So let us see how we have performed testing, assembly, and the entire video of how the product post welding, how the product looks. So this is a video. Before getting into, let me show you the complete video. Here we are going to weld two ports and the end cover, or the end cap, what we call. So this is a machine exactly like what you've seen the design, built it. So there's another tag, this is Nikit here, there's Kalki, who's our channel partners for welding machine. So just start this process. Yeah, as we press sequence on the control panel, what you can see here is there's a sequence switch, the mushroom button for emergency, there's main on and off, there's an indication, and weld on and off manual switch. Now the sequence has started, it's moving to about 180 degrees, then it moves back again to about 270, then moves back to 360 plus a 10-degree overlap for about, that will be about 360 plus 10, 370. You can also manipulate it to 390 if you want. and this entire sequence happens with a 4-axis interpolation. The controller used here is a 6-axis interpolation one, but what we are actually utilizing on the machine for the sequence right now is a 4-axis interpolation, where x-axis, y-axis, z-axis and the torch rotary align itself based on two major criteria, that is the parent diameter or the mother diameter, what we call, of the tube, and then the child diameter, that of the port. So if you have a mother diameter of 80 and if you have a port diameter of, let us say, 25, you just input these two values. So our program converts that into a profile, a curvature profile, where it will trace the component's depth at which it has to weld, because a normal circular welder cannot fulfill this criteria. You need a particular curvature to happen so that it fills the bottommost portion of the port. Now what you can see here is we finished 2 ports welding, and now the machine is moving back towards the component end where the entire component or the job rotates. So we have the end cap welding done. So the end cap is fixed here basically by pre-tacking, and then the system rotates the cylinder and welding happens. As you can see, the job is rotating. It's moved from 0 degrees to 90 degrees. You can see there's a V groove that they've divided as the joining groove, where they want the actual deposition of close to 6 to 8 mm to be welded or to be deposited. You can also have weaving done here. There's an inbuilt switchover for weaving and for oscillation. The same. So that's it guys on the port and end cover welding. Let's look at how we're going to weld the block. Welding the block. Okay, now so that was the first machine. This is the second machine with a different collet or the fixture. And if you see, since the diameter is less, we have increased the speed also based on the diameter of the port as well as of the component or the mother diameter. First port gets welded, now it moves to the second port. Basically the deposition is really high here because that's the criteria where they've given a certain gap and they wanted us to fill the entire gap. So this particular welding. Now both ports gets welded, the component rotates to about 180 degrees or 120 degrees where the mounting blocks are placed, which are pre-tacked. The entire pre-tacking of mounting blocks and the inlet and outlet ports are done in a different fixture and loaded onto the machine. Now, as you can see, one portion of the linear weld is done. Now the curvature of the block is being welded. I'll just speed it up a bit so that it's clear. It's a pretty slow process because initially when we started testing this particular program, we thought let us do it in-house with a much slower RPM, then we can increase it. Right now the speeds can be varied up to 100 mm per second, but the weld video that you're looking at runs at about 10 mm per second to about 12 mm per second. So as it finishes block number 1, it moves to the second block where first it welds the curvature. Basically the 4 components or the 4 phases of each block. One is the curvature phase 1, then linear phase 1, curvature phase 2, linear phase 2. All the 4 are being welded here. So once all the 4 faces gets welded, we have both the blocks which are completely welded. You can also see the kind of finish that we have given. Finish always depends on the current and the voltage and the speed of the system that you have set. Now moving back to the port welding component, I would like to show you how post welding, how the port looks with the kind of overlap that we had set. This is the kind of weld width that we have achieved on the port. Basically, you can also see the overlap there. It's a bit big, yeah, but then you can always decrease it Basically the overlap angle and the overlap delay contributes for this particular big plot. But overall, if you see the entire phase of the weld, it's really good, and the kind of pressure that it takes care of is up to 300 bar. That's the tested pressure. Now moving back to the last phase, that's about costing. Now for the entire project, the cost incurred, let me put this up, put this across. Okay, so here we are. The process is MIG welding. It's a steering cylinder welding automation. Process is MIG welding, and the costing for it is here. It's a 6-axis motion control system, 7-inch display panel, costing $3,200. There's a linear 3-axis assembly which costs about 2250. That's about $2,250. It covers X, Y, and Z axis. The next thing is torus rotary axis assembly, where A axis, it's about $683. Fourth component is the job rotary axis, that's our B axis, it's about $2,560. Basically the load that B axis can withstand is up to about 65 kilos. And the next thing is torch and torch adapter assembly, costing us $175. Then is the fixture assemblies, basically a collet, spring steel material based collet for a single cylinder, costing us about $1,190. Then the final portion of it is basically frame and safety system. For frame, it's $1,760. For safety system, $650. Now one thing that you should always look at is, guys, power this system consumes. In any automation, power is a very important factor. Not today, but all through the year you run the machine, you have a very good average with our kind of system, because we use only stepper and the power consumed is hardly 650 watt hour. So the total BOM cost would be $12,468. Now, since you all know that we classify our costing into two, inclusive and non-inclusive. For non-inclusive, we've not included labor, any kind of labor, that is design, procurement, inspection, assembly test, electrical testing, and training. Next, the company overheads depends on individual companies. Consumables, basically this doesn't vary much. Welding bar source, welding wire, gas, and tungsten. Here we're not using tungsten, but here we're using only the welding wire. Now, power consumption, insulation, packing, and forwarding. All these factors play a very important role, guys. And yeah, so that's it for today, and we would like to wrap the show up. Hang on for our next episode. Thank you so much, guys.